I am going to experiment on coupling and isolation characteristics of microstrip directional coupler. The aim of the experiment is to determine the coupling and isolating characteristic of microstrip directional coupler, and the objective is to understand the coupling and isolation characteristic of directional coupler. The operators required are microwave signal source with modulation, which is ranging from 2.1 to 3 GHz, attenuator pad, coaxial detector, VSWR meter. VSWR stands for voltage standing wave ratio, matched loads, which is around 50 ohms, directional coupler, which is also called as microstrip parallel coupled coupler, ranges from 2 to 3 GHz, and connecting cables. Coming to the theory of directional coupler, a directional coupler is a 4-port reciprocal plus passive network. The basic function of the coupler is to sample power flowing in one direction in a transmission line and reject power flowing in opposite direction. This figure shows the schematic of a directional coupler. Here, port 1 is input port, port 2 is direct output port, port 3 is coupled port, and port 4 is isolation port. The properties of an ideal directional coupler are: all the terminations are matched to the ports. 1. The power travels from port 1 to port 2. Some portion of it gets coupled to port 3 but not port 4. As it is also a bidirectional coupler, when the power travels from port 2 to port 1, some portion of it gets coupled to port 4 but not port 3. If the power is incident through port 4, a portion of it is coupled to port 2 here, but not to port 1. If the power is incident through port 3, a portion of it is coupled to port 1 but not to port 2. Ideally, the output of the port 3 should be 0, but practically a small amount of power called back power is observed at port 4. This is the setup of directional coupler. Here we have to assemble the setup as shown here. Measure the reference power level by connecting the cable one end at P and Q respectively. Here, set the frequency of the source to 2.3 GHz and increase the RF power output of the source till VSWR meter shows the reading in the range 45 dB. Increase the frequency of the source in steps of 0.1 GHz from 2 GHz to 3 GHz and note down the corresponding readings in the VSWR meter. So, in this meter we have to note down the corresponding readings. Here, two things we have to measure. First thing is coupling and the other thing is isolation. To measure the coupling, insert parallel line coupler between P and Q with the port, that is input port connected to P, and port 3 is called the coupled port connected to Q. Terminate port 2 and port 4 of the coupler with a 50 ohm matched load. record the readings of the VSWR meter for the frequencies which is mentioned from 2.223 gigahertz. Using the calibration graph, get the corrected value of port 1 to port 3, and the coupling can be calculated with the calibration graph from port 1 to port 3. Next thing is to measure isolation. Connect the parallel line coupler between P and Q with port 1, which has input port, connected to port P, and port 4, which is isolation port, connected to Q. Terminate port 2 and port 3 of the coupler with 50 ohm matched load. Record the readings of the VSWR meter for the frequencies mentioned from 2.223 gigahertz. Using the calibration graph, get the corrected value of port 1 and port 4. Isolation can be calculated by subtracting the calibrated value of the graph from port 1 to port 4. Here we have the tabular column. So, record the readings from 2.1 to 2.8 gigahertz. Port 1 to port 3 is for to measure the coupling, and take P1 dash, P3 dash, which is the calibrated graph, and coupling is calculated while subtracting P1 to P3. So, P1 dash minus P3 dash gives the coupling characteristics. To measure the isolation characteristics, record the frequency VSWR meter ranging from 2.1 to 2.8 gigahertz from port 1 to port 4. Using the calibrated graph, record the readings, that is corrected value of the graph, that is P1 dash and P4 dash, and isolation can be calculated by subtracting this P4 dash from P1 dash. So, P1 dash minus P4 dash gives the isolation characteristics. This is the experiment on microstrip directional coupler. The outcome of the experiment is student will understand the coupling and isolation characteristics of directional coupler. Now let us move on to the demo. Let us see the determination of coupling and isolation characteristics of microstrip directional coupler. This is the directional coupler. This directional coupler frequency ranges from 2 to 3 gigahertz, and here we are giving input from the source signal 2 to 3 gigahertz, and this is the output port. So this is port number 1, port number 2, port number 3, port number 4. In the port number 3 we are going to measure the coupling characteristics. In the port number 4 we are going to measure the isolation characteristics. And here we have the matched load. The matched load is about 50 ohms. So to connect the matched load to the directional coupler, here block the output port and the isolation port. Now we are going to measure only the coupling characteristics, and as we did in the ring resonator, the connections have to be made using the detector. So connected using the detector. Now the connections are made as shown here. Again, vary the frequency from 2 to 3 gigahertz. Turn on the RF. Let us vary the frequency from 2 to 3 gigahertz. As we vary the frequency, here we can see in the VSWR meter, we can see the output changes. and we have to note down the readings. This is port 1 to port 3, which is the coupling characteristic. To measure the isolation characteristic, we have to switch the matched loads to the isolation port. Connect the matched load to the coupling port, pin number 3, and connect the attenuator to the port 4. Now we are going to measure the coupling characteristics, isolation characteristics. Now the connections are set for isolation characteristics. Again, vary the frequency from 2 to 3 GHz. Turn on RF. Vary the frequency from 2 to 3 GHz from the signal source. As we vary the frequency, we can observe there is a change in the VSWR meter. And we have to note down the readings. Now, after taking the readings from the VSWR meter, the same readings have to be done in the calibration graph. In the calibration graph, if signal frequency is 2.1, if the VSWR meter reading is reading about around minus 55.2, then here we get minus 55.2. So the same readings have to be plotted here. So we get the corrected value. The corrected value may be, it is minus 55.2. So you may get around minus 55.2. So we have to correct the value using the calibration graph. Thank you.